the next module, module 2. So here we study the first topic in the module 2 is qualitative description of current flow at PN junction. So the module 2 name is PN junction. So here forward and reverse biased junction. In that first topic, qualitative description of current flow at junction. The first topic. So before understanding the qualitative description of current flow at PN junction, we need to understand the basic concept of what is PN junction. A PN junction is a junction formed with a P-type semiconductor on one side and a N-type semiconductor on the another side. As you can see on the figure, that is PN junction. So when we are saying it as a PN semiconductor material, so that material is formed by adding a pentavalent as well as a trivalent impurity to a pure intrinsic semiconductor. So when we combine the P and N, there is a junction will be formed in between them. So that is a PN junction. So on the right hand side, there is an energy band at equilibrium. So this energy band at equilibrium, here we are dealing with a three condition. So one at equilibrium, so when this PN junction, when we are not supplying any voltage, so that is at a equilibrium. So this one is here we are not giving any external supply. So this is like this. We are not giving any supply for this PN junction. So at this point, so the energy bands, how it looks, that we have to study. So before studying the energy bands, we need to understand, we already studied conduction band, valence band. So in between them, energy gap will be there. So if we consider a P-type material, so how will be the Fermi energy level for a P-type material, and if we consider a N-type material, how will be the Fermi energy level? So here, so we know this is valence band and this is our conduction band. This is the energy gap that will be between the conduction band as well as the valence band. The Fermi level is always above the valence band for a P-type material. Got it? In case of a N-type material, the Fermi level, if this is the valence band and this is a conduction band, so the Fermi level is exactly below this conduction band. So that is shown over here. So if I put one line between a P-type as well as a N-type, so the same thing, which is P and is there, no? The same thing. P is on the left side and N is on the right side. So the conduction band is a top band, we call it as a conduction band, and the bottom band we call it as a valence band. So this is a conduction band. So if we consider a N-type, so similarly refer this one. This is our Fermi level. The dotted line is there, no? This is Fermi level. The Fermi level is exactly below the conduction band. And if you refer the P-type material, the Fermi level, you can see here the Fermi level is exactly above the valence band. That is, the Fermi level is exactly above the valence band. So P-type is nothing but a majority are the holes. And if you consider a N-type material, the majority are the electrons. That is, a free moving electrons will be there, that will be exactly below the valence band. In case of a conduction band, so in case of a P-type material, the majority are the holes. That holes will be present exactly above the valence band. That is explained here. Clear till here? Next one. What happens at PN junction? As you can see, when we combine a P-type as well as a N-type material, there is a formation of a depletion region. What happens at depletion region? The electron from N side diffuse through the junction and combines with the holes. So the electrons which are present in N-type material, that will diffuse and combine with the holes in the P side. So whatever the electrons which are present in the N side, they diffuse through the junction and combines with the holes in the P-type. So when these electrons diffuse through the junction and they combines with the holes, there will be a formation of a negative ions in the P region. Similarly, the holes which are present in the P region, they diffuse towards through this junction and combine with the electron and form positive ions in the N region, as you can see. But there is a limit up to which they can form the positive as well as the negative ions in the P region as well as the N region. So what we can say before this one, as if you refer this above picture, so here we have a holes, but that holes are depleted and they are converted into a negative ions. Here we have a electrons, but that electrons are depleted and they are converted into a positive ion. So depletion is nothing but a vanishing. So vanishing process occurs at that place. For that reason we are calling it as a depletion region. So the current which is produced because of the diffusion of a non-uniform charge carriers, that current we are calling it as a diffusion current. So that diffusion current is from P to N, as well as a electron diffusion current is from N to P. Till here clear now? That PN junction there is a formation of ion. So there is one limit up to which that electrons can combine with the holes. After that what happens, if the electrons which are coming after formation of this region, if electron try to diffuse through this junction, they will get repelled by the negative ions. So up to one point the diffusion layer, that is a positive as well as a negative ions formation, will be there in a PN junction. So that theory is given here. Next term, diffusion current. So the non-uniform concentration of moment of charge particles, that is the diffusion layer, whatever the happening, no. So because of the moment of extra charge carriers in the N as well as a P region, that current we are calling it as a diffusion current. And there is one more current, that is a drift current. As you can see here, if in a depletion region, as there is a positive as well as a negative, if a positive as well as the negative ions are present, then we can say it as there is a formation of an electric field. So that electric field we are calling it as a barrier potential. So because of this electric field, so there is one current, that is a diffusion current. One more current will exist in the PN junction, that is a drift current. So what happens if we consider a p-type material in the sense, so all holes will not be there, so minority charge carriers will also be there. The minority charge carrier in a p is a electron. Similarly, if we consider a n-type, the majority charge carriers are electrons, the minority charge carriers are holes. So the minority charge carrier, they wander around and they will come back to this junction. So when they reach this junction, so because of the electric field, they get swept again back to the p-type. So whatever the electrons, the minority charge carriers which are present in a p region, they will be wandering inside this p region. When they reach this junction, because of the electric field, they get swept again back to the n region. So what we can say here, this process is exactly opposite to the diffusion process. That's why drift current as well as a diffusion current are exactly opposite to each other. Getting my point? Diffusion current and drift current, two currents. So diffusion current is because of a non-uniform charge concentration of charge carriers. That is from P region to N region, the ion formation is there. No, that because of the diffusion, there is a existence of current. That current we call it as a diffusion current. And one more current is a drift current. So that drift current is exactly, the process is exactly opposite to that of a diffusion current. That drift current, the charge carrier moment is there, no, that is under the influence of electric field. So he can see here that the current is under the influence of electric field. So that is exactly opposite to the drift current. So two types of current. So here the direction of a current is also very important. Next, barrier potential. So barrier potential is nothing but the depletion region potential is there, no? If a depletion region, because of positive as well as a negative ion, there is existence of a potential. That potential we are calling it as a barrier potential. This barrier potential there is one limit. So after that it will oppose the movement of further electrons to the region as well as the further holes to this depletion region. So it will oppose. So that opposition is nothing but a barrier potential that you can see here. Positive charges present at N side and negative charges present in the P side of PN junction acts as a barrier which prevent the further movement of electrons and holes. So there is one particular barrier potential for different type of a semiconductor material. For example, silicon, it is typically 0.7 to 0.7 and for germanium it is 0.3 volt. Okay, next one. So here you can see we need to in the next slide you can see the three conditions of a PN junction at equilibrium. So what is the barrier potential and what will be the energy band. Similarly for forward bias and for the reverse bias. Now we study each one by one. So the first case is this one at equilibrium. So at equilibrium what happens, we are not connecting any voltage source to a PN junction and W is the width of the depletion region and this is P type and N type and the electric field. So the direction of electric field is from positive to negative. So if this is the P type, so positive ions are formed over here in the depletion region. If this is a N region, negative ions are formed in the P region that we studied in previous slide. So always the electric field is from positive to negative. That's why the direction is given in this way. Understood? Next one. So this is about the at equilibrium. Now this is barrier potential. About the barrier potential, here the barrier potential is explained by considering a 1 coulomb of charge. Assume that 1 coulomb charge which is present in this P region, that has to move from P to N region. 1 coulomb charge has to move from P region to N region. So as we are not applying any electric field, so when the 1 coulomb charge which is present in a P region, that we are calling it as a VP. That is a potential of the particular charge in a P region, VP. That is a neutral potential. So when it reach to the junction, so if we draw the line, vertical line, so these graphs are along with the P as well as the depletion region and N region. So the below energy band is also the same thing. You need to use a scale to draw these diagrams. So when it reach the depletion region, so what happens, its kinetic energy reduces and potential energy increases. That increase in potential is given by this increasing slope. So once it gain the potential energy, again it will flow in the N region. That is a Vn is a potential after gaining, that is a Vn is the barrier potential of the N region after gaining potential energy. Clear? Vp and Vn. So here V naught, that is the potential Vp between a Vp and a Vn, that is a barrier potential is there, no V naught. So that V naught is nothing but a depletion region potential E. Now energy bands. So the same thing, if we draw the vertical lines, okay, so this is our P region and this is our N region. So as I told you earlier, the Fermi level, along with the Fermi level we are drawing this type of a graph. So the Fermi level, this is our Fermi level, that dotted line. So EFP is a Fermi level of a P region, EFN. This will be clear for you. EFP is a Fermi level of a P region. This is P region and N region, and this is our depletion region. So depletion region. Okay. EFP is a Fermi level of a P region and EFN is a Fermi level of N region. As I told you earlier, the Fermi level is, and energy bands we know. Conduction band, valence band. Okay. So this is our valence band, and the top we have our conduction band. So for N region, the Fermi level is exactly below this conduction band. So this is our conduction band, no? The Fermi level is exactly below the conduction band. Similarly over here, how we can draw this one is, first we have to draw the Fermi level as well as the conduction band. So for a N-type material, the Fermi level is exactly below this conduction band. Similarly, for a N-type, P-type material, this Fermi level is exactly above this conduction band. Okay. So then the same thing, if this is our valence band, the below is our valence band, obviously this will be our conduction band line. Similarly, if this is our conduction band, so somewhere here will be our valence band. So you can refer the N, wherever N is mentioned in the subscript, no, that is nothing but a N region, P is nothing but a P region. So if we join these two lines, so that is a decreasing slope in the depletion region. So that completes our energy band graph for the equilibrium condition. So what we can say, at equilibrium, the Fermi level, the dotted line is there, no, it is same for N region as well as for P region. But if you refer the right side diagram, the Fermi level, there is a gap that we study later. So one more thing, whatever the electrons, the energy gap between the here is, that is represented as the charge times the barrier potential voltage V0. Charge times the barrier potential voltage V0. If electrons which is present in the conduction band over here, if it has to move to the P region, then it has to gain Q into V0 times of energy, then only it will move to the P region, that it indicates. Clear for the equilibrium condition? Now here the same thing, the current direction is also given. See, in exam you have to draw the current direction also. Particle flow and current flow. In a previous class we studied there will be two types of currents will be flowing in the, and if we consider any semiconductor material. Particle flow, that is nothing but a hole moment, electron moment, that we call it as a particle flow, and a conventional current motion. Okay. The first one, here the four terminologies are used. First one is a hole diffusion. Hole diffusion. The first term, that is over here, the hole diffusion. How the hole will move. So that is nothing but if we consider a PN junction, PN, where we have a hole will be, one second. Again I will draw the PN junction. So this is our P and this is our N. So the first terminology, first one is hole diffusion. So holes will be present in the P region. So the hole will always move from this side to this side. That's why the arrow mark is given like this. Okay, the first term. And one more thing, in last class we studied electron moment as well as a hole moment, conventional current and electron current. So we always, the conventional current is there, no, exactly the same direction of a hole current. Remember the point, the direction of a current is always same as the hole current. So that's why the current direction is in the same as that of a first one, hole diffusion current. Understood this one? First terminology is a hole diffusion. This one, hole diffusion. So that is from P to N. So hole will move from P to N. So that's why the arrow mark is like this. And the current direction is exactly same as the hole direction. The first one is clear, no? Now the second terminology is hole drift. This one. The second one is hole drift. Again we consider a PN. Hole drift, we just now we studied diffusion current and a drift current, two terminologies. If a hole diffusion is in one direction means hole drift will be exactly opposite to that of hole diffusion. Getting my point? This is hole diffusion. The current of direction is also hole, same as hole. Hole drift is exactly opposite to that of hole diffusion. That's why it is exactly opposite to that of hole diffusion. And a drift current, that is again a hole drift current, is exactly same as that of a hole drift moment. See, conventional here, whatever the current is there, no, it will move exactly the same as a hole motion. If this is a hole moment, then this current is also in this same direction. If the drift is in, that is a hole drift is in this direction means the current will also, the drift current is also in this direction. The third terminology is electron diffusion. Electron diffusion. Now you tell me, if this is a P and this is a N, okay, the third terminology, what it says, electron diffusion. This one, electron diffusion. So electron will diffuse from N to P, no? That's why the dotted line here we represent by dotted line. So the electron diffusion in this way, okay. And similarly, the fourth terminology, what it says, electron drift. So electron diffusion as well as electron drift, they are exactly opposite to each other. Drift and diffusion, now you have to remember one thing, drift and diffusion opposite to each other. The current is always the same as hole current. Now, if this is the diffusion of electron, then current direction will be exactly opposite to that of a diffusion of electron, because whatever the current is there, no, this current is same as hole current. If electron is moving in this way means the conventional current will move in this way, because if this is an electron movement means hole will be moving in this way. I hope this is clear for you. Now for the second condition as well as for third condition we study now. So at equilibrium and the barrier potential is over now, and energy band is also over, that is at equilibrium. Now consider the first case, at forward bias. What will happen? Under forward bias, as name says, P region is connected to positive terminal, N region is connected to the negative terminal. Refer this diagram. P is connected to positive, N is connected to the negative. So the whatever the applied voltage is Vf voltage, and the electric field is in this direction. Okay. Now the Vf, the whatever the applied forward voltage is there, no, that is always flow from positive side to a negative side. What you can see here, the electric field is exactly opposite to each other. So because of that reason, the depletion width is there, no, that will decreases. Again I will repeat. Here P is connected to positive of the external supply and N is connected to the negative as shown in the figure. So what happens here? The depletion width decreases. Why this depletion width decreases? Because of the forward voltage. This depletion width is greater than this depletion width. Next one, barrier height. This one, barrier height, the second graph. Barrier height is V0 minus Vf. In the previous graph at equilibrium, so this was the potential, that is a neutral potential, but here if you draw the horizontal line, you will get to know the difference. So this amount of difference is there. So it will, this is a neutral voltage, Vp is a neutral voltage. Now it will gain some voltage because of applied electric field. Here we are applying the electric field. For that reason, it will not be at the neutral voltage. This is the neutral point, neutral voltage before applying the electric field. Now it will shift upwards. Shift upwards by some value. So that value is because of applied electric field. Now, So that here this graph is explained by considering a 1 coulomb of charge moving from P to N. No? Similarly here, 1 coulomb of charge moving from P to N region, what will happen? That 1 coulomb of charge move at a junction, what happens? It will gain potential energy and it reduces the kinetic energy. So it will gain potential energy. For that reason, this slope, increasing slope, then with that potential energy, it will move in the N region. Here the barrier height, this height is V0 minus Vf. The total height that we know V0, that is from this figure. The total height is V0. So this height, how much it is shifted, no, that is Vf. If we subtract that one, so that will be the voltage, that is the height of the barrier potential. Till here it is clear, no? How we got V0 minus Vf? The height of the electron energy barrier is simply the electronic charge Q times the height of electrostatic potential barrier. That is, that we study here. Now, if you refer the energy band diagram, the Fermi level for the N region is not same as Fermi level for the P region. P region and this is N region. So here the Fermi level is the same line, but here it is not the same line. So N region will shift upwards. That is nothing but a Q times Vf. So this gap is nothing but a Q times Vf. The Fermi level gap is there, no? So that gap is the height of the electron energy barrier is simply the Q times the height of electrostatic potential barrier. Thus the bands are separated by Q into V0 minus Vf under forward bias. So here the Fermi level will not be the same line, so it will shift upwards. But in case of a reverse bias, it exactly opposite to this of forward bias. So it will shift upwards and the rest of all is same as that of a previous case. If it shift upwards means here also we have a the whatever the shifting of energy is there, no, that one is because of here the shifting of energy is there, no, that is because of applied electric field. Under forward bias, the Fermi level on N side is above and Fermi level at a P side is below by Q into Vf. So this difference is there, no? So that difference we are calling it as a Q times the applied electric field, Vf. Rest of all it remains same. So the difference between the conduction band energy of the P type to this conduction band energy of N type, this band gap energy is there, no? That is Q times the barrier potential which is present over here. Here Q times the barrier potential which is present over here. Here also the Q times the barrier potential which are present in the above graph. Clear till here? What it says, if an electron which is present over here, if it wants in the N region, if it wants to shift to the P region, then it has to gain this much of energy. What it's that point is explained here. Now the same thing again, the how will current flow and how will drift current and how will be the conventional current, that we have to study now. Diffusion current. Here you can see the length of the current also. Here this length is not same as this length. This length is not same as this length. Here length we are increasing. The length is increased now. Why? That is because of applied electric field. With forward bias, the barrier potential is lowered. The difference in potential is lowered. So this potential is lowered in the sense more electrons in the N side of conduction band have sufficient energy to diffuse from N to P over small barrier. So what it says, so why we have a lengthier current direction, that is a more diffusion current we have, more diffusion hole current and more diffusion electron current. This one, more diffusion electron current. So why this length is more is because here the barrier potential length, this amount of length is lesser compared to this one. Here Q times V naught. So this length is higher, but this length is smaller. So this much of energy is required to move the electron from N region to P region. So we call this as N region and this as a P region, no? So electrons which are present in a N region will need Q times V naught minus V of energy to move to the P region. So that much of energy is required. As this energy is less, so more number of electron as well as the diffusion will takes place from P to N as well as N to P. So diffusion current is more. Now, how will be the direction? The whole diffusion. Same, consider the PN junction, that is above mentioned in the particular forward bias. Whole diffusion, the first term is whole diffusion. Whole will move from P to N, whole movement. That is from P is nothing but a majority carriers will be present in a P, no? So this is our whole movement. And how will be the electron whole movement? Okay, first one whole movement, and current direction exactly same as whole direction. See, current direction is nothing but a whole direction. Electron as well as the current direction is exactly opposite to each other, as well as the drift and diffusion is exactly opposite to each other. Now, the second term is whole drift. If a hole is moving from this side to this side, means exactly opposite to this will be the drift. Again, you can refer here, the length is same as previous one. Here, by applying the electric field, there is no change in the drift current. It will remain same. Now, the third point is electron diffusion. So, electron will move from N region to P region. So, that's why it is like this. And the current is exactly opposite to the electron flow. The last one is electron drift. Drift current as well as the diffusion current are opposite to each other. That's why it is in opposite direction. So, electron drift in the sense the current will be exactly opposite to this one. Electron is inversely proportional to current direction, as well as the diffusion current is exactly opposite to the drift current. This you have to remember in order to draw the direction, particular direction. This is very important. Now the third case, reverse bias case. In reverse bias, as name says, P side is connected to the negative supply and N is connected to the positive supply. You can see in the graph, P is connected to negative supply, N is connected to positive supply, and that voltage, supplied voltage is Vf. That is applied in a reverse way. So that's why minus Vf is mentioned in the V is equals to minus Vf. Now what happens to the depletion region? Here the electric field is from positive to negative. Here the electric field will be in this way. So both are in same direction. That's why the depletion region is more. Here the depletion region is less. Here the depletion region is more. Barrier height is V0 plus VR. About the barrier potential now. Here this one is a neutral potential. This is one potential, that is a neutral potential. This is by applying the electric field Vf. So how much it is shifted by Vf times. Now similarly here it has to decrease by minus Vf. That's why below we have shown here. So this is the potential of a P region, that is Vp. Now the same thing, 1 coulomb charge is moving from P to N region, means it will come under the depletion region and it will gain the potential energy. After that, with the same potential it will move in the N region, the same thing. Now, so this is the V0. So the entire voltage will be, till here it is V0. The barrier potential height, so this height will be V0 plus Vf, sorry, Vr, we call it as a Vr. For a forward bias we call it as a Vf, here we have to mention it as a Vr. So the V0 voltage, till here it is V0. V naught plus the reverse voltage, which is VR. V naught plus VR is the barrier height. Clear, no? Next, about the energy band. Exactly opposite to that of a forward potential, we need to draw this one. That is, the band are separated at Q times V naught plus VR under reverse bias, then at equilibrium. So the length, that is the how much value it is shifted above, is Q times Vf. So that much value it is shifted above. Similarly here, Q times VR, that is Q times VR. So that much of voltage is shifted below here. Clear, no? Here Q times Vf, it will shift upwards. Here in a reverse bias, Q times VR, so it will shifted below. Getting my point? The only difference is in the Fermi level of N region. Rest of all remains same. Now what we can say, that is the energy required for the electrons which is present in the N region, it has to gain this much of energy to cross this depletion region and move to P region. That what it says, Q times V naught plus VR. Now come to the particle flow and current flow. Particle flow is nothing but a hole moment, drift, electron, hole, electron drift, hole drift, hole diffusion, electron diffusion. That we call it as a particle flow. And the current flow is exactly same as a hole drift, hole diffusion. No, the first term is hole diffusion. Again consider the P-N region. Hole diffusion is from P to N, but you can see here the length is smaller compared to this one. Why? Because the energy is required to diffuse through the depletion region is more. That's why the diffusion current is less, because the depletion width is more here. The width in the beginning case it was only W. Here it is reduced. Here the depletion region is widened in the reverse bias. So it requires a more amount of energy to cross that depletion region. That's why the current is less. Similarly, the current direction is also small, because hole diffusion is exactly same as current direction. So it will also be in a small. Now the second point, hole drift. Hole drift is exactly opposite to that of hole diffusion. That's why opposite sign. And the current direction is exactly same as hole drift. Okay, but you can refer the drift magnitude is same in all these three cases, because this drift is not getting affected by applied voltage. The third one is electron diffusion. So the electron diffusion is from N to P. That's why this is electron diffusion is from N to P. That is dotted line, it is indicated. Now electron drift is exactly opposite to this one. Similarly, the current direction will be exactly opposite to this one. Till here it is clear, no? Equilibrium condition, forward bias and reverse bias. So the theory is given over here. You have to draw all this theory in your exam. Similarly, in a reverse case, forward case and at equilibrium case. Now, drift current. So I told you diffusion current and a drift current. There is one more topic will come under this qualitative description of current flow in PN junction, that is a drift current, that is we call it as a generation current also. This current is mainly because of minority carriers present in PN region. If we consider a simple PN, means there will be a minority charge carrier, that is a holes, electrons will be there in a P region. Similarly, here also the minority carriers holes will be present in the N region. So under the influence of electric field, that is a depletion layer electric field, they get swept by again back to the P region, and electrons which are present in the P region, they swept back to the N region. So that exactly opposite to the diffusion, drift current is flowing. Drift current is because of electric field. Okay. So this drift current will be depends upon the EHP rate, that is electron hole pair rate. So that depends upon EHP generation. So the EHP are generated by thermally exciting the semiconductor material, then there will be a more EHPs. So this generation current, which is same as a drift current, which is equals to the electron hole pair. So this drift current is mainly it will play a role in reverse bias condition. Now at equilibrium, we know diffusion, if you refer the current direction in the previous figure, here the drift current as well as the diffusion current, the length is exactly same. The drift current length as well as the diffusion current is exactly same. Why? Here we are not applying any electric field. So whatever the current which is present in the semiconductor material is without applying the electric field. So that's why at equilibrium what we can say, I current which is flowing in the semiconductor material at equilibrium, that is at no bias, I drift current is minus I generation current, that is I is equals to I diffusion current minus I generation current. I diffusion current minus I generation current. This is I generation current. So why we are taking this magnitude is, we know diffusion current and drift current are exactly opposite to each other. That's why the minus sign is given. So as we already given a minus sign, in order to avoid the confusion, we are considering it in a magnitude value. Getting my point? So this current, no, there is no current when there is no bias for the PN junction. Okay. Now, when we apply the forward voltage, what will be the current flowing in the PN junction? That is in this case. So the first case is over now. No current flows in the, because both are exactly opposite to each other and the magnitude is same and exactly opposite to each other, that is a diffusion as a drift. So no current flows in the reverse, that is at equilibrium. And what happens at forward bias? At forward bias, the current in the junction, that is current flow in a junction, is given by I is equals to I naught into e power qv by kt minus 1. So why this exponential term is considered here is, if you refer the VI characteristics of PN junction, you can refer this one as well as this picture is not clear, I consider one more figure, that is this one. As you can see here, we are drawing the graph with respect to voltage and current. That is, when we supply the positive voltage, the current will also starts to increase. So this is the current which is increasing exponentially. That's why the equation is given in that manner. I is equals to I generation current into e power qv by kt minus 1. So here if we supply V is equals to Vf, that is positive Vf, we call it as a forward bias current. So here this is the picture of forward bias. Here if we substitute in the above equation, that is in this particular equation, if we refer V by minus V, that is nothing but a VR, that is a reverse voltage. If we substitute in this particular equation, that is exponential term is negative, e power exponential is negative. So e power exponential is negative, for that reason we are neglecting this part. So if we neglect this part, the remaining part will be I is equals to minus I generation. So that's why at reverse bias, the current, as we increase the voltage, irrespective of the, with respect to voltage, the current will be flowing, that is in the negative direction. So this is the equation for the current which is flowing in the PN junction. If V is equals to positive, so this is a exponentially varying current. If V is equals to negative, this term is very negligible. So I is equals to minus I gen. I is equals to minus I generation current. So irrespective of the applied voltage, if I apply the reverse voltage, then current will be same magnitude. So if I keep on increasing the voltage, irrespective of the voltage, it will be constant with some negative value, that you can see here. VI characteristics of PN junction. Clear, no? You have to draw the graph along with the terminologies. You have to explain in exam. So this completes VI characteristics of PN junction and qualitative description of current flow at PN junction.